All right, so I want to thank the organizers for inviting me. I'm happy to be here. So I'm going to be talking about some developments. So about Wittferential algebraic geometry. So this is essentially differential algebraic geometry where you replace the usual derivative operator with a thing called a p derivation or a Boolean derivation, and yeah, so I'm just going to kind of jump into this. So the plan of the talk is going to be in three parts. So first I'm going to spend quite a bit of time explaining what differential algebraic geometry is, and in particular try and transition to these Witt vector operations. And I think a really good illustration of this is Boolean's proof of Mann-Mumford, and how the Greenberg Transform slash these p-jet spaces slash arithmetic jet spaces can be used for Diophantine results. Then at the end, I am going to talk a little bit about how you can use these extra operations to build perfectoid spaces, and the relation to perfectoid theory via prisms and via this new kind of completion that's in a paper of Boolean and Miller. So that's kind of the ramification part of the talk, and it's going to be kind of minimal. Let me say that if I don't get there, there is another talk that is at 1 p.m. Pacific or Mountain Time on Saturday by Alex Boolean, and he's going to be talking about this result here, and some of the weird constructions that they've been able to do using these arithmetic jet spaces. Okay, so let's start. And so I'm going to ask, what is Wittferential algebraic geometry? And so I'm going to start with differential algebraic geometry. And so for me, differential algebraic geometry means two things. Okay, so first it means, in a general sense, it is just algebraic geometry using extra operations. So you're not just looking at solutions of polynomial equations, but you're looking at solutions of differential polynomial equations, so differential algebra, or difference equations, so things with a ring endomorphism, or you could have a p derivation, so there's kind of a zoo of operations that you can be using, and they're all kind of related. So that's differential algebraic geometry in a general sense. And there's also the classical sense of the word, which is just differential algebraic geometry where you have like a single derivative operator. So this is about rings with extra operations. And the two big examples that I want to talk about are, a field with a derivation. So you could take univariate rational functions and say the derivative ddT that everybody knows. And then you could talk about a field with a Boolean derivation, a ring with, so this should be a ring with a Boolean derivation. And so the classic example of one of these operations that acts kind of like the derivative on the integers is the Vermont quotient operator. All right. And so what's the idea here, or how can you remember this? So by Fermat's little theorem, n is congruent to n to the p mod p. And so it's going to be p times something, and you just divide by p and just take that something. So kind of both the numerator and denominator are 0 mod p. But it is not a thing that goes to mod p. It is a thing that goes from the integers to itself. Okay, so now I'm going to talk about the most basic thing that you can do, which is kind of the set theoretic version of the Zariski. So this is the version of the Zariski topology for classical differential algebra, that is with the derivative operator. Okay, and so so suppose we're given a differentially closed field. So this is the, so sometimes you do algebraic geometry over algebraically closed fields. You can do differential algebra over differentially closed fields. The situation gets much more complicated once you start talking about rings with extra operations. And this is where the connection to model theory comes in. So for example, so the types in usual algebra, or in algebraic geometry, right, or polynomial equations, if you have an algebraic element, it's determined by its minimal polynomial, right? And the conjugates really all act the same. You can't distinguish them. In differential algebra, so a type is determined by an equation and an inequation of lower order. So you have some differential equation, and then that an element satisfies, and then you have an element something that doesn't satisfy. Another weird thing about differentially closed fields is that for every differentially closed field, there's a subfield that's also differentially closed. That's weird. Not every algebraically closed field has a proper subfield that is algebraically closed. So the field theory gets a little bit different. So it's already getting weird. But so if I take just like a usual algebraic variety, say over this field, one other thing that I wanted to say is that that meromorphic functions. So any countable, there's a theorem of Seidenberg that says any countable differentially closed field is contained in the ring of meromorphic functions. So it's safe to think about those. Okay, so if I just take a subset of points of this, then what you can do is you can take the Quotient closure, which is essentially the same thing that you do with the Zariski closure. You take all the differential polynomials vanishing at this set, make the ideal, and then take the set of points that is vanishing there. So this is kind of non-trivial already. Already you can take interesting sets in usual algebraic geometry or arithmetic geometry, and you can get interesting Quotient closures. So the classical example would be, okay, so this says the Manin kernel, but it's covered, my face is covering it right now. But essentially what's going on is that, so if you take the torsion points are no longer dense in this finer topology. And so what I'm wanting to say with this slide is that, that you can cut out more things using differential algebra. Isogeny classes is an example. Torsion points, a lot of these kind of special point situations, you can cut things out that you normally wouldn't be able to cut out in a non-trivial way using a finer topology. Okay. All right. Okay, so I wanted to give you an example of a differential algebraic variety, right? And so what are some things that you can cut out, right? So if we just take the affine line, right? So here's another thing that you can cut out. You could cut out, say, the constants. Okay, so let me just say the purpose of this example is kind of to illustrate all the kind of basic constructions by means of an example, right? So, okay, so I have a differential equation. I can cut it out. And so this is the constants of so like the constants of a derivative. And the way that we write it out is we kind of formally adjoin a new variable, and so we make the prime a new variable, and then we cut out a subscheme of the thing that we made with new variables. Okay, so this is what's called the first jet space. If we had, instead of done the affine line, we had done we added extra equations, then we would take the derivatives of those equations as well. So this is the first jet space. This is the trace of this differential algebraic variety, and it cuts out an order 1 differential equation in there. Okay, so yeah, so this is the point is that these things, the schemes here correspond to subschemes of the big of these things with extra variables. So we've turned this differential algebra problem back into scheme theory, but in higher dimensions. So just continuing with this example, we didn't need to go to order 1, right? So what you can always do is take these equations and then make it something in an infinite number of variables. And the way to do that is you just formally adjoin the kind of like the free derivatives of everything. And then you close up the ideal under taking derivatives as well. Okay, and so you get this thing here. This is still finite dimensional. And it's still isomorphic to the previous one, the sigma one. But yeah, this is how this procedure goes. Okay, so you can close things up in this way. So yeah, and so okay, so where's the non-algebraic part of this? So it's like, how do you determine membership? So if I have a point in my original variety, right? How do I determine whether it is a member of the constants or this differential polynomial? So or this differential variety. So A is in here if and only if the exponential of this thing is in this guy here. So that should be fixed. That should be a sigma 1 for this particular example. Okay. Well, there's the 1. Okay, yeah, and so this is the exponential map. So there's a map from the points of your scheme, which are differential algebraic, so they have a derivative operator, into these jet spaces by taking derivatives of the coordinates. Okay, and really that's the only non-algebraic map, and everything can be factors through this one non-algebraic map. Okay, so the general features of this example are kind of persist, is that differential subvarieties of X are cut out by subschemes of an Rth jet space, or some jet space. Okay, and that membership, as I said before, is determined by the exponential. Okay, so what you do is you take So what you do is you take your points, then you take derivatives of those points, and then you plug those into the equations with the derivatives in them. Okay, and then the other thing is that once we prolong, if we take a variety and then we start taking derivatives of the equations, once we take an infinite number of derivatives of the equations, right, the variety itself starts to have an operation on it, right? So yeah. Okay, so I just wanted to hammer down what the Rth order jet space is for a single differential ring, just so you guys know what I'm talking about. So in the affine case, we'll have, if we write this in kind of the tuple notation, right, where we have a tuple of variables, and this ideal is given by tuple polynomials, right? So the coordinate ring here is of the Rth jet space is given by taking derivatives of the coordinates and then taking derivatives of those equations. And then, so if K has if the coefficients of F of these polynomials have derivatives on them, you take derivatives there as well. So the derivative, the universal derivative prolongs the derivation on K. Okay, and so in the global case, so how do we do this globally? So this particular construction localizes. So for other operations don't localize as well, and so some things need to be done. One of the things could be, say, p-adic completion in the case of p derivations, and then we glue things together in the usual way. And so one thing you could do is you could say take global spec, all right? So you could take, so you could do this construction, then perform global spec, and then you'd get these jet spaces. Okay, so yeah. All right, so now I want to move into the p derivation setting, where things are very similar, right? And I'm going to do kind of a comparison of derivations and p-derivations, or these delta operations, right? And so in one side, I'm going to have derivations, and then on the other side, I'm going to have p-derivations. Okay? So, all right, so what are the primary examples to keep in mind? So we've already talked about, the univariate rational functions with its derivative operator. And we've talked about the integers with, I haven't talked about this, but there are the integers with this Fermat quotient operator. Okay, so this is the primary example. I guess I said this before, right? So what are the rules here? So just like we have a product rule and a sum rule, there is a product rule and a sum rule for p-derivations. So that's kind of one of the key ingredients of this business, is that you can express derivatives of sums and derivatives of products as polynomial expressions in the lower order, polynomial expressions and derivatives of the two inputs. Okay. One thing that I do want to mention is that the p-derivation here, so that polynomial there is integral, right, on the right-hand side. So the binomial coefficients cancel, and that's a polynomial with integer coefficients. Okay, and so associated. So now I kind of want to go to this general picture, because I thought that Andrew would be interested in this in particular. Is that so derivations are associated to dual numbers. There's always a ring scheme floating around, and p-derivations are related to Witt vectors in a way that I'm going to explain. In a similar fashion, power series are, when you take higher order derivatives and then you take a limit of those, you get a power series ring. And similarly for Witt vectors, you get these full p-typical Witt vectors. Okay, so this is a ring that you can have. And so, all right, so I'm going to kind of describe what derivations are. So a derivation on a ring A is the same thing as a section of this natural projection. So there's this ring of dual numbers, right, has a map where you send t is equal to 0, right? And so what you can look for is I can look for sections of this map which are also ring homomorphisms. Okay, so what's the proof of this, right? So what's the bijection between these two things? So if I have a section, right, then we can write it like this. And this kind of already spoilers. The second part is going to be there. And so, for example, like things like the product rule are encoded by the ring homomorphism property, right? So you just have to use that when you multiply this out, that t squared is equal to 0, and then equate the coefficients of t, right? So, so this encodes the product rule in disguise. Okay, so similarly, right, for p-derivations, right, there is, so p-derivations correspond to p-typical Witt vectors. So p-typical Witt vectors and p-derivations are friends. And it's exactly the same thing, right? And now it depends on whether or not you want to take the derivation, the product rule and sum rule for a p-derivation to be, so we kind of axiomatize the rule for the p-derivation before. So it's something with a sum and a product rule, as described before. That's what a p-derivation is. And so you can either take that those sum and product rules as the axioms, or you can take the definition of the Witt vectors as the fundamental quantity. Okay, so if I take the Witt vectors of length 2 and I take two components like that, right, then the second one is what a p-derivation is. So if you ever forget what the sum and product rules are for p-derivations, you can always remember it by the way that it relates to Witt vectors. Okay, so the product rule looks like this, or the Witt vector multiplication rule looks like this, and the Witt vector addition looks like this, where this polynomial here was the same error term in that polynomial before. Oh, I can't really. Can I move myself in the middle of this? Okay, so that's what we have. All right. So, all right. Okay, so now I kind of want to talk about kind of a general, very general setup that kind of shows that all of these derivations and p-derivations are instances of a kind of a general construction. Okay, and so I thought Andrew Coben would like this, since I saw him talk at Stanford about coalgebras, and so the main point is that rings with extra operations are controlled by affine ring schemes. Okay, and what I mean to say is that, okay, so what's a ring scheme? So a ring scheme is a scheme whose functor of points spits out rings. It's like a group scheme. So the functor of points of a group scheme spits out groups. And in the case of affine group schemes, so affine group schemes are spec of H, where H is a Hopf algebra, right? So, and so what's a Hopf algebra? So a Hopf algebra is a ring, right, which has a co-multiplication and a co-unit. And it has some compatibility properties with its addition and multiplication. And so this is an operation which takes the ring into the ring tensor the ring, right? And so instead of multiplying where you take two things and you go to one, you take one thing and you go to two. It's like the opposite of addition. And so yeah, so for birings, so birings have a co-addition and a co-multiplication. So there's two operations there. And when you're given a biring like this, so you get functors from the category of rings, commutative rings, to the category of commutative rings. So let me say a little bit about my notation here. I'm using kind of like the MacLane notation, where I'm using the category for the Hom set as well. So there's relative versions of this as well, but I'm going to suppress that in this presentation. Okay, so how do you get addition and multiplication? Well, if I want to add two things, what I do is I use the co-multiplication on the biring, or co-addition on the biring Q, and I use the co-multiplication on the biring Q. Okay, so this is example. This is how you get. So normally Hom sets in commutative rings are not rings, right? But in the special case of a biring, they are. All right, and so once you have one of these, you can do this thing where you take sections of this projection, supposing that you have a projection, right? And that gives you your extra operations, right? But there's more, okay? So I just wanted to kind of write down in completely, so you can see this, or you can do it yourself. This is an easy exercise, is to show that if I take this biring with the identity operation, and so what we do is we think of these birings as housing the operations, right? So they're like a ring of operations. And when you multiply them, they're kind of, you could think of them as like point-wise addition of the operations, okay? So this thing has these co-multiplications. E is like the identity operation. So so maybe you should call Z adjoin E like O, right? So it just spits out if you put in a ring, it spits out the ring again. Okay, so these are the rules here, and there's co-units like this, and then you can check that this biring that I wrote down actually gives you the dual number functor, right? So every f over on the right hand side is determined by where it sends E and where it sends the D, right? And so that's two things already. And then if you work out what the co-addition and co-multiplication are, you see what the ring homomorphism is exactly this, right? So this is the isomorphism is written as I show right here. Okay, so you can do the same thing with Witt vectors. So it turns out truncated Witt vectors are representable, and infinite Witt vectors. So for every truncation, for Witt vectors of length 1, 2, 3, 4, whatever, Witt vectors of length 0, which is essentially the identity ring scheme, and the full Witt vectors, those are all represented by ring schemes. Okay, ring schemes over the integers. So how do jet spaces fit into this general formalism? So so here's the theorem. So this is an operation done by Borger and Wieland. So if you're given two commutative rings in a biring Q, so there's an adjunction. Of course, this is functorial, but I didn't write it as functorial. But just like for tensor products, Hom of so Hom and tensor product. So the tensor product operation is the left adjoint of Hom, right? From a module, right? We have an adjunction here for birings, and this operation here on the left is called the composition product, right? So what it encodes is this encodes the jet spaces. So if I have Q and I have an A, right? So if I want to take the jet space of spec of A, right? Well, that is spec of this, okay? Sometimes they localize, sometimes they don't localize. And so there's things so there's always a functor of points, but it may not be a scheme. And there's things that need to be done to fix this. But in the affine case, these are the jet spaces. And this functor over here, this is like the dual numbers of B or the Witt vectors of B, or some truncated Witt vectors of B. That's what we have. And just like if we took A to be equal to B, the right-hand side, if they were sections of the projection, this would be derivations, and then this would also be derivations, right? So this thing is also kind of like the Kähler differentials in that morphisms out of this thing are like derivations from A to B. All right? Okay, so jet spaces in general. So now if I just take HQ to be the functor represented by Q, right? And this is what I said before, is that in the affine case, right, that the jet space is this spec. And in the and then you have this functor of points property that is a lot like Weil restriction, where the points of the jet space are the Q points of B. So I'm just rewriting the previous slide in geometric notation. Okay. All right. So let's look at this in an example, and I just kind of want to do something fun so you can see that this leads to interesting things. All right, so I want to give an example here. And so in the case of derivations, right, so I'm going to motivate something that I studied. So in the case of derivations, right, this thing is just the tangent bundle. So if this is for a single derivation, right, so here you have the dual numbers here, and everyone knows that the tangent point. This is out of order. I'll fix this. So this is the tangent bundle. So the functor of points for the tangent bundle is this dual number valued functor. Okay, I mentioned the relative case. Sometimes if you were to fix a derivation on the base and then use prolongations, which is another way to do this, then this thing becomes a torsor under the tangent bundle. So that's another thing. The torsor class is a Kodaira-Spencer class as well. So when you change your ring scheme, you'll be changing. You can think of it as maybe like changing a Kodaira-Spencer theory, right? So you're deforming the deformation theory. Okay, so in the case of Witt vectors of length 2, right? I'm going to do this as you get some weird tangent bundle. So that's one way you can think about this functor of points. So instead of just being dual number valued points, they're Witt vector valued points. So this is the scheme version. You can also P formally complete. That also gives you Witt vector points. But this gives you a weird tangent bundle. And let me kind of show you the kind of things you can do, right? Is that so like I said, oh, so this animation is correct. So we get some weird tangent bundle, and okay, so the sub example here is if I take G to be a group scheme, then the first jet space is also a group scheme, and and then this map which projects down, right? So there's this map here, and this is a group homomorphism, right? This is just like if you take the tangent bundle of a group scheme, that's also going to be a group scheme, right? And the map from the tangent bundle of a group scheme to the group, right, is a group homomorphism, right? And so one thing that's interesting is the kernel of this. And so there is a whole theory of Lie algebras, right? So associated to these arithmetic, there's an arithmetic version of Lie algebras that you can develop. And some of this was developed by myself and Alex Boolean in a 2014, I think 2014 is too early. It may be a 2016 paper. There's a series of 3 papers, and this is the sort of thing that we look at. And we were looking at, what we could mean by like a linear differential equation in the arithmetic sense. Okay, but there's a zoo of things that you could do and study using these group schemes. And so, okay, so the whole point is that for each biring, right, there is one jet space. In the corresponding classical case, right, so you have to add more operations and then you get higher order jets, right? That's the way this goes. So it's not just like there's one thing, but there's a sequence of them. And then eventually you know the infinite version of this is what Borger and Wieland call a plethory, and that corresponds to the infinite jet space. So in this business, once you go to this infinite thing, which is something that you want to do because you kind of want to differentially close your ideals, this is you can see that you start to get into non-Noetherian territory. Okay, so this is some comments about Witt vectors. I don't think we need that. All right, so now that we've talked about jet spaces, I want to talk a little bit about Men and Mumford. And the way to start, I guess, is to start with the statement. And it says that for a curve x over the algebraic numbers, then there's other versions for other fields, that if it has genus bigger than or equal to 2, then the number of torsion points on the curve is finite. So this is when you have a curve and I stick it inside its Jacobian, there'll be it'll intersect the torsion points in a finite number of places. All right. So the first proof of this it was by Renault in the 80s, and I'm going to talk about a proof that uses p jet spaces due to Boolean. Before getting into it, I want to say a little bit about why this is kind of a remarkable statement. So, okay, so in what follows, we're going to let A denote the Jacobian of x, and I'm going to draw the Jacobian like so. And what we're going to do is we're going to stick the curve inside of the Jacobian, and like this. So here's the curve inside the Jacobian. And what's interesting is that the torsion points are dense inside the Jacobian. So there's many of them, and I'm going to let this animation draw. And so the fact that there's so many points, it's kind of weird that the curve doesn't hit any of them. I mean, I guess it's not weird because it's a theorem, but it's saying that the curve doesn't hit any of these algebraic points, these torsion points. Yeah, and they're dense. Okay, so All right, so what I'm following here is so a mixture of two papers. So there's this Geometry of P-jets paper by Alex Boolean, where he introduced arithmetic jet spaces for the purpose of solving this problem. He had already done some stuff with the relative, he had some Diophantine applications of previous results in the 90s using differential algebra. And so, motivated by those previous results, he wanted to extend the differential algebra to arithmetic so he could prove number theoretic things. Okay, so the Boolean's proof starts with two ingredients. The first one is that so for p greater than large enough, right, which is a prime of good reduction, then the torsion points that are on the curve are actually in QP unramified, right? So there are algebraic points, and they are So this is like QP adjoin the roots of unity, which are whose power is prime to p. Okay, and so the other piece of information that we need to get this proof going is that the specialization map is injective when restricted to torsion points. So to know a torsion point is to know the torsion point mod p squared. Okay, you'll notice that I've been switching between QP and ZP. And so what we're really doing is we're using the Neuron model of so we're using a model, right? And so we're using primes of good reduction, and we're using the Neuron model at the prime of good reduction here. Okay, that's all I want to say about that. I mean, I guess you could just take the Picard scheme of a curve over a DVR. And to avoid, so we could have done this over C, or we could have tried to do it over C. Once there's transcendence degree, once you have some transcendence degree, you can actually use the differential algebra results, the classical, the derivative differential algebra results, and so for simplicity, we're gonna start with something over Q bar, so we don't have to worry about extending the base. Okay, some things about Witt vectors real quick is that so the Witt vectors of length 2 of a finite field are z mod p squared, and over fp bar they're zp unramified mod p squared. And if you go to the full p typical Witt vectors, it's zp unramified completed. But I think everybody here knows that. The other thing is that there's for p torsion free rings, lifts of the Frobenius in p derivations are equivalent. Okay, so that and they're given by the formula that's related here. And the lift of the Frobenius here just acts on the cyclotomic parts by raising all the roots of unity to a power of p, and then extending linearly and completing. Okay. So, so now we're going to talk about the application of jet spaces. How do jet spaces appear in the story? Well, we talked about this adjunction property, or the functor of points for these jet schemes, right? And, so if I take the z mod, the zp unramified points, z mod p squared points, that's the same thing as the Witt vector valued points of y. So for over fp bar, so those two rings are the same, and so that's the same thing as the jet space there. So when you do it with characteristic p rings, sometimes this is called the Greenberg transform. Okay, there's another way to think about this, right? About this map here, that has to do with the exponential that I was saying. So one thing you can do is since zp unramified completed has a p derivation, right? What you can do is you can take a point, and then you can take derivatives of the coordinates of the points, or arithmetic derivatives of the coordinates of the points, and then you can so that gives you this map here, right? And then so one thing that I wanted to mention is that this map here is a group homomorphism when y is a group. All right. Then, so then you can take that and then you can reduce those, you can specialize again and reduce the points mod p. So this is another way that you can view, this is how another way that the jet space points can come into the play. Okay, yeah, and I said that this was the specialization map. Okay, so the proof, okay, so now I'm going to start to, so we talked about how the jet space is involved, and we talked about that we only need to really look at the torsion points mod p squared. And so the way that this is going to work is I'm going to use some properties of the jet space of the abelian variety, and I'm going to use some properties of the jet space of the curve. And because the jet space of the curve is contained in the jet space of the abelian variety, what we're going to have is essentially we're going to have this situation where the torsion points are going to be needed to contained in something that's proper, right? But proper is and then the torsion points on the curve are going to be like the fact that any points on the curve are going to be needed to contain in something that's affine, and so you have something that's affine plus proper, and then so when you intersect those two, then it becomes finite, and that's the way that this is going to go. Okay, so I want to describe why the torsion points are contained in something proper. Okay, so we already know that this extension here is finite index because multiplication by p is an isogeny. And all right, and so what you can do is, so this thing is covered by finitely many cosets of that thing, right? And that also means that the torsion points in here are going to be contained in finitely many cosets of the torsion points in the jet space of that p times things. Okay, but so yeah, the torsion points is contained in finitely many cosets of this, and what we're going to show is that the p times the jet space thing that's proper. All right. So so the claim is that this subscheme is proper. And here's the proof idea, right? So it turns out that there is that these arithmetic jet spaces. So this thing here looks like, so okay. We talked about the Lie algebra before. This is the Lie algebra, the kernel of this, and like the arithmetic Lie algebra. And it turns out that the arithmetic Lie algebra in this case of an abelian variety looks like some power of the additive group. Okay, and if we're doing it mod p, right, then multiplication by p on the additive group is essentially the zero operation. Right, so so this kills. So multiplication by p kills this part, and okay, so multiplication by p kills this part. So that means we get to quotient. So this thing factors through a quotient of this, which means that so p times this will factor through a quotient of this, and then quotient by the additive group, which means we get the proper thing there. Okay, so yeah, so again, this is what I just said, that multiplication by p kills the additive part. All right, so now this kind of explains the proof why p times jp, that's contained in a proper subscheme. And so what do I want to say about that? So yeah, so okay, that's all I wanted to say, is that it's contained in a proper subscheme, and you can actually count the number of translates. The other thing that I wanted to say is that for x over r, which is a curve of genus bigger than 2, let's smooth, right? And then we have that the first jet space is affine. Okay, the proof idea, it comes from the presentation of torsors. So it turns out that the first jet space is a torsor under the Frobenius tangent bundle. The cohomology class that classifies the torsor is what I call the Delaunay-Lousy class. It's like an arithmetic Codier-Spencer class. It does appear in the Delaunay-Lousy theorem. Okay, so once you have a torsor under a line bundle or a vector bundle, right? You get an X'd class, right? Because you have H1 of X in the vector bundle. That's the same thing as X'd of X'd of O X into the vector bundle, right? And then that gives you some extension. So you can either do it, you can either say it's an extension of the dual of that by O, or you can extension of O by the other thing. So there's kind of two dual concepts here. Either way, right, when you have these torsors, there is, so you can take the projectivization of the vector bundle that's the extension, and then remove the, part of the extension, right, which is the, this Frobenius tangent bundle thing. And this is the Frobenius cotangent bundle. So it goes in the opposite way. So yeah, so this is a general setup, and it turns out that this is going to be ample, right? And which means that that this thing is going to be affine. So I mean, when I say canonical line bundle, I don't literally mean like the canonical line bundle, but this is the line bundle associated to the jet space. So this should actually not be line bundle; it should be vector bundle. So it's rank 2 for the case of a curve. But these things exist in general, and so this object is this what we call the total differentials in this paper with Ketz, Zirk, Brown, and Rabinov, and in Saito has another paper that kind of builds off of what we did. So we kind of did. There's kind of a formulation of a Gauss-Manin connection in this arithmetic context. That's kind of an aside. Anyway, this ingredient appears in this proof, and it helps you prove that the jet space is affine. All right, so now we have the ingredients that we want. We have this proper piece, we have the affine piece, and because you have affine and proper, then you get finite. Okay, so again, we take these torsion, the points, and we stick it inside the jet space, and then we have the jet space of X intersect a closed subscheme. So this is this piece is affine, right? Then we had the proper piece, so that's the subvariety of the jet space of the abelian variety, mod P, that's proper. And then you get that if you have something that's affine and proper, then it's finite. Okay, so that's the proof. Okay, so I want to make some remarks now. So one remark is that so doing this, you could be a lot more careful, right? And you can do intersection theory. You can compactify so you can use that P of E thing, right? So you can compactify and then start to do intersection theory, and this allows you to get explicit bounds on the number of points, right? There's an interesting open problem here that has to do with these P's that I'm underlining here. And a conjecture of Mazur is that there should be a bound that's independent of P. Okay, and we don't know if that's true, but the problem here is that so you need to somehow deal with singularities, right? So you don't want to make the assumption that you're going to a large prime of good reduction, and then you want to deal with the singularities. And this is something that I've thought a little bit about, but it broke. So, but it's an interesting problem nonetheless. Okay. So the other thing that I wanted to say is that this method is connected to Chabot-T, and so the paper to look at is this p-adic differential characters, this Inventiones paper by Boolean, where he defines kind of a Chabot-T looking map where the kernel contains finite rank subgroups. Okay, so these are like these Boolean-Manin maps. Yeah, so that's that's all I'm going to say about that. Okay, so now with my very limited remaining time, I am going to talk about this Boolean-Miller construction of perfectoid spaces using arithmetic jet spaces. Okay, and so so the main slogan that I think is useful and is kind of like, this is a direct application of this, is that if you ever want to do something, if you have a technique where you use the Frobenius for something in characteristic P, but you kind of like want to use it in characteristic 0, there is a free construction of a scheme with a lift of Frobenius, right, which is the infinite jet space, right? So this infinite arithmetic jet space automatically has a lift of the Frobenius, and you can use that to your advantage. I mean, in my experience, it's like almost anything, you can, I mean, of course you can try anything that works in characteristic P and characteristic 0, right, using this method, right? So, and as you see, this is a useful idea. It's not just like for sport. A lot of times you need to do this. Okay, so again, so in what follows, I said that this ring R, I'm just going to use this ring R to be ZP unramified completed. This is the full P-typical Wood vectors of the algebraic closure of a finite field with P elements. It's just a ring that I'm just going to use. It's an auxiliary thing. That's not so important in what I'm going to say. It's just to make things simple. Although this is how the Boolean and Miller do it in their paper, and I don't think it's really important at all. Okay, so I wanted to talk about the infinite jet ring. So this is this thing that I was saying is that if you have something, if you have a ring and you want a lift of the Frobenius, this is how you get your lift of the Frobenius. Is you make this ring, right? So what you do is you take your indeterminates, right, and then you just kind of keep adding derivatives to them, and then you take what am I going to say? So then you take derivatives of the coordinates. So in this version here, I'm going to work P formally. So this is the p-adic completion of this of the the polynomial ring in R variables. All right. So okay. Another way to view this is that this is the infinite jet space, but P formally completed to of this ring. Okay. So one of the things that's cool about this is that this ring has a lift of the Frobenius, right? So it has a P. So I said for P torsion-free things, lifts of the Frobenius and P derivations are the same. So the universal P derivation here is just y. You take y prime, y to y prime to y prime prime, et cetera, et cetera. So you just have kind of like done this free construction that makes it so that ring homomorphisms out of this give you derivations, P derivations from A to something. Okay, so yeah, so this is the ring that you get that has a free lift of the Frobenius. Okay, and so the perfectoid ingredients here are well, there's this ring that we all know now, which is you take pth powers and pth roots of p, and then you join infinitely many of them, and then just a little note to myself. And then there's okay, on this ring here. So the hats here will denote p-adic completion, p-formal completion. So there's this phi map, which is extends the lift of the Frobenius on the Witt vectors, this ring R, but we're just going to specify that it's linear on these pth power things. So mod p, this is not a lift of the Frobenius, okay? But mod m, the maximal ideal, it is a lift of the Frobenius. So modulo the maximal ideal of this ring. Okay, so there's these two pieces here. So sorry, this is the perfectoid thing. So you have this ring, then you have a lift of the Frobenius on it. Okay, so what I can do now is I can do something that is kind of weird, right? So given one of these finite type rings over R, it could be you know, like the formal version, or you can take a you know, just literally a ring instead of just like formally finite type. I don't know what you call that, but just generators modulo relations, right? Then what you can do is they make this functor that's p infinity of a, which gives you a perfectoid ring, a perfectoid K0 algebra with a lift of the Frobenius, right? So lift of the Frobenius p derivation is the same thing. So what you can do is you can complete along it's kind of like localizing at the Frobenius, so that adds a bunch of Frobenius roots, and then it turns out to be perfectoid. And just a couple remarks on this is that this extends to schemes. And it gives kind of a lift. So when you reduce it mod p, it reduces to a usual perfectoid construction. And then another thing that's kind of interesting is that there's an interesting interaction between morphisms in the category like delta morphisms which involve derivatives. So these are just essentially maps from the jet space down to another scheme. So, and there's a little bit of like descent data hanging around in their construction, but I'm not going to say anything about this. But okay. Then finally, I wanted to just give a comparison between prisms. Okay, and there's kind of I don't know, it's worth comparing. Okay. And I guess another thing to say is that prisms in prismatic cohomology are inherently, they involve p derivations, and they're a Wittferential construction, right? So what they do is they look at a ring with a p derivation and an ideal, and they demand that this ring is complete, and which is not a very big deal with respect to this topology. So like if you did, this formal power series rings would be one. And then you ask that P be contained in the ideal plus the Frobenius of the ideal. Okay, so that's maybe a more serious condition. But again, this phi here is the lift of the Frobenius associated to a p derivation. So p derivations, lifts of the Frobenius are friends. They're the same. So anytime you have a p derivation, you automatically have a lift of the Frobenius. And if you're p torsion free, then the converse also holds. Okay, one more thing that comes up in their theorem is that this thing's called perfect if the associated lift of the Frobenius is an isomorphism. Okay, so a perfect prism is one of these things which has this completeness condition and has this condition on the ideal. And then it's perfect if if the phi is an isomorphism. Okay, and so the Bott-Schulze theorem, it gives you an equivalence of categories between the category of perfectoid rings and the category of perfect prisms. And then, so they have a category, so in the Boolean-Miller gives a way of generating the category of perfectoid K-algebras. And so it's unclear to me how much of the Boolean-Miller construction can be broken down and how these two things are related. But they're both ways of generating perfectoid rings. And, of course, theirs is an equivalence of categories. Yeah, and I guess that's all I wanted to say about this. Alex Boolean might say more later. Maybe not. But thank you for coming. And here's an advertisement for Alex's talk.